Okay, I'll get started. Thank you everyone for joining today. Welcome to our Mastering Sterile Cycles webinar. I'll introduce myself quickly. So I'm Sophie Lambert, Sales Manager at Wolf Labs. I've been at Wolf Labs for just over 10 years. I'm always available to help if anyone's got any queries or needs a quotation for anything. After this session, I will be sending an email to you all with a copy of a recording of this session. So if you miss anything, or if you want to share it with any of your colleagues, you will have it to hand. You'll also have all of my details on there. So if you have any further questions, then feel free to ask. There's a question and answer section at the top and a chat section. So if anyone has any questions throughout the webinar, or anything that they would like to say, feel free to put it in there. And when we get to the end, I'll go through and I'll read all the questions that we've got. And hopefully Paul will be able to answer all the questions you've got. So today we have Paul. He will be talking to you about how steam sterilization really works, best practices to keep your team compliant and safe, and a few things in between. So I'll hand over to you now, Paul, if that's okay, and you can give everyone an overview of what you'll be covering today.
That's great. Thanks, Sophie. Yes, thank you very much for the opportunity, and welcome to everyone that's on the call. Just to introduce myself, I'm Paul Birchmore. I work for Astell Scientific, autoclave company, and I'm happy to share some of our knowledge with you, and hopefully there'll be some good questions and a good session to be had. So my section will be about 30 minutes, running through, as it says on the screen there, those points, how steam sterilization works, how to carefully and safely load and operate an autoclave, choosing the correct cycles, some common issues, which we'll hopefully cover as we go through all of these points, best practices, how to keep you and your staff safe. And then finally, right at the end, a piece about how there's a new acronym for you, EDS, Effluent Decontamination System. It's a new idea, relatively new idea, but it's specific to sterilization of contaminated liquids, which I'll touch on in more detail shortly. So without further ado then, let's get started. Steam sterilization. So autoclaves use steam, the heat of steam, to kill bacteria in a contaminated load. Principles of sterilization have not changed in the past 150 years. The monitoring systems and the ways of checking effectiveness have evolved, but the principles are very similar to a pressure cooker in that sense. So why steam? In order to kill a cell with heat, its temperature must be raised to a degree at which the proteins in the cell wall break down. Steam is a very efficient medium for heat transfer, which makes it an excellent way to destroy microbes. Compared to air, on the other hand, is a very inefficient way to transfer heat energy. And the difference between steam and air is a thing called vaporization or evaporation. So it takes 80 kilocalories of heat energy to bring 1 litre of water to its boiling point of 100 degrees. It would require another 540 kilocalories to convert that litre of water into steam, which means that the steam at 100 degrees contains 7 times as much energy as water at 100 degrees. Now that's a big significance, because when that energy, that's how we effectively use that energy, that latent heat in the steam, to be so effective at destroying the microorganisms. The big advantage is that when the steam is in contact with a microorganism, bacteria, it condenses back into water, and all of that energy is released. It's that process of changing state from steam back into water. As it hits a bacteria, it cools, the steam condenses, and all that energy is released. That's what breaks down denatures the protein that destroys the bacteria's cell walls and thereby kills the bacteria. It's far more efficient than, oh, sorry, I should just add, it's typically going to be we're going to hear this throughout this PowerPoint. There's a number of little video clips in it that talk about nominal. So if I make it simple, you can do sterilization at a variety of temperatures, but the one you're going to hear constantly is 121 and for a duration of 15 minutes. And it gets nicknamed the nominal temperature and duration. So just to clarify, that will come up a couple of times on the video. But at that temperature, the steam has released all of that energy back into the cell, thereby destroying it, denaturing it, and you have an effective process. And you can do it with air, but it's, as it just touched on, there's no vaporization, there's no condensation, there's no change of state. So hot air is by no means as effective. You'd have to do it for longer and at a higher temperature to get the same result. So that's why steam is such a popular and well-known and well-used method for sterilization. So a load, different types of load will be found in the lab, whether it's a university research lab or a medical facility or any other, a variety of quality control or microbiology labs. And it's considered sterile once it's gone through a full sterilization cycle. Now that will be made of heating up time, a holding time at the sterilization temperature, and then a cool down phase. So that's what we call the cycle, the temperature sterilization cycle. But once the load is sterile, you can just be confident there are no more live bacteria, live microorganisms that would cause havoc in a sterile environment, such as a lab or a hospital or a food production facility, etc. But the different types of loads are touched on. Those are typical popular ones listed on the screen there. They can be sterilized, as I've touched on already, at different lengths of time and at different temperatures. But you're going to hear this phrase, I'm going to mention it again, the nominal 121 for 15 minutes is the sort of default setting, if you like. And what we're also going to find out is that the process of sterilization will have different component parts within the machine, depending on the type of load that we are going to put inside the autoclave. So we'll go through those one by one. And you'll see sometimes that there's mention of additional features that need to be included within the autoclave design to achieve a sterile condition for some of these types of loads. So we need to know what the load is and then have the appropriate features within the autoclave to allow you to complete the process effectively. Most common one is glassware. If it's clean and empty, it's really no problem. You put it in the autoclave, you run the cycle. There is nothing to be concerned about or need to mitigate against. The most popular, perhaps in laboratories, research laboratories, is sterilization of fluids, culture media, but also sterilization of contaminated liquids and fluids that are now going to be discarded. So you've got clean liquids and you've got dirty liquids. Worth just pointing out that this is going to come up right at the end. This is where this acronym of EDS has crept in, particularly for waste liquids. I'm going to mention something that at the end of the presentation might help you consider an alternative way to sterilize liquids that are contaminated rather than the more standard way of loading them into an autoclave bottle by bottle. So I've got a number of clips here. A colleague of mine has been able to demonstrate the effectiveness of some of these features. So I'm just going to hit play on this one. Already the phrase nominal has come up, but just to point out, that's the sort of standard settings. Bless him, Neil keeps using the nominal phrase, but as I've touched on already, it will keep coming up. Just to reinforce that point that Neil made on the video there, the 80 degrees C media loads are hazardous, and if you can't anymore, there's a legal requirement within the control systems that lock the door above 80 degrees, so you can't open the door above 80 degrees. But if you could, then in theory, the sudden reduction in temperature and pressure could create conditions whereby the media, if it's in high enough in the bottle, could re-boil basically, and you'd have red hot media being created inside the chamber, which would be extraordinarily dangerous. So there are very clear reasons why you monitor the temperature, and the door will not unlock until the media itself is below 80 degrees C. On there, I think on very old units I've seen in some facilities which are probably more than 10 years old, there was a key switch idea which allowed you to unlock the door, perhaps for a non-media load, which meant it could be abused almost. But that isn't a facility that's available on newly made units. There's a statutory requirement now that you can't open the door. Yes, just to make the point that Neil's making there, you're monitoring the temperature of the media with all the bottles with the same volume of media and the control bottle having the same volume of liquid, then everything is equal. When you change the size of the bottle and you change the size of the liquids in the bottles, then the uniformity of the temperature increase isn't consistent across the different size bottles. So that's one just general point to make. You want consistency across your sterilization of your completed cycle, then use the same bottles. Don't have a mixture of sizes of bottles. Don't use mixtures of sizes of loads of liquid within the bottles, if you see what I mean. Be consistent and have small quantity of one type of bottle with a type of liquid media inside it. You could reset the controller to have that cycle as a standard setting. In most cases, these microprocessor control systems, you can then add another cycle to have a different size bottle with a different size media in it, and have another cycle to do that load. So don't be tempted to mix and match. Keep it simple. Keep the bottles the same. Keep the liquid volumes the same. Also, bear in mind, everyone uses Durand glassware, but if it was a type of load which was going to be used in a propylene bottle, then again, those things will change the characteristics of the heat up time. So glassware heats up at a very different speed to polypropylene. So you wouldn't want to mix and match the types of bottles or the types of glass and containers within the load as well. So keep it consistent. Same size bottles, same size volumes within the bottles, same bottles, and then you won't have any inconsistencies in your process. So just to sort of simplify that even further, what Neil was drawing attention to with his initial bottled media loads is that's typically done in an autoclave with what we call heated inside the chamber, which I could also simplify by saying it's a wet chamber. It's got water and heating element inside the chamber. That means that the whole chamber will contain water. There will be water at the bottom of the chamber. I'm going to call that a wet chamber. The enhancement that Neil mentioned takes the heating of the water to make steam outside into a separate, what we call a steam generator. And then you have some extra features as well. That I'm going to call a dry system. So you've got the two types. You can use the wet system for, in this example, the media prep. But as Neil pointed out, you could use an enhanced version, which I'm going to call the dry version for media prep. You could use either system for this type of load. The advantage is the dry system can be significantly quicker for the cycle. With a media load, a lot of time is taken for cooling down at the end of the cycle after the sterilization part of the process. And with the enhancements, you can speed up that cooling part of the cycle. So for some labs who have a high throughput of bottled media and they really need to optimize the process, then adding those extra features would enhance the cycle time overall over one load to over a number of loads during the day. Obviously, it's not insignificant, those extra features, and they could add significantly to the overall budget required for that product, as much as 30% perhaps. So you don't do it lightly unless you need to justify it, unless the cost balance equation sort of works out in favor of higher productivity. Just to emphasize something Neil touched on there, something called air ballast. When you use such a system with these enhancements, which has a cooling jacket, that's a very quick way of bringing the media in the bottles down in temperature. In some ways, the cooling jacket can be too efficient. It can bring the temperature and the pressure down very quickly. And the reduction in pressure could give rise to reducing the boiling point of the media, hence you get a boil over again, which is hazardous and wasteful. So in order to prevent that, we counterbalance that, adding air pressure back in again, it's called air ballasting. So you prevent that massive reduction in pressure in the cooling phase, thereby prevent any overboiling of the media itself. So some of these features are interlinked. So you need to make sure that you have all of the features, as it were, to allow you to safely speed up the process. So then moving on, so moving on to another sort of very standard type of load that's going to go inside the chamber, waste plastics or discard. In most cases, it's let's call it biohazard 1 and 2, but it's potentially up to number 3 biohazard level, BSL 3. We stop there. In some very specific labs in the UK, there may be a requirement for BSL 4, but in our laboratory product range, we go up to 3. So again, over to the video again. Probably just take a slight issue with Neil's video there. I wouldn't recommend putting your hand inside a discard bag. He was only doing that to demonstrate the sort of open aperture of the bag itself. I might even go further and say, don't even constrict the bag at all. Maybe fold it over the top of the discard bin. Perhaps even slash the bag if it's already sealed from transportation between the laboratory and the location where the autoclave is, then even tear the bag or cut the bag with a knife. And this is all about allowing the steam to penetrate into the load, particularly discard loads, which have a variety of interlocking shapes, potentially can trap air. Air is the enemy of a successful sterilization cycle. So you need to ensure that the air is able to get out and the steam is able to replace that air straightforwardly. You don't want pockets of air trapped in the system that could cause them to be sort of released later in the cycle that would then drop the overall temperature below the sterilization point, and that would cause the autoclave to register that and confirm us a failed cycle. So good practice is to ensure, see the problems before they arise. Note that if the bag is a particularly compacted load, then make every effort to sort of open the bag or cut the bag to ensure that there's access. And obviously there are some scenarios in that photograph where the correct container of the bag isn't used, and for some peculiar reason, the bag is put inside the autoclave without any containment around it, no discard bin in which to put it, and that would only mean that all of the items within the bag will just fall into the base of the autoclave, as that photograph shows, making quite a hideous mess. So you need to use the correct equipment to load the bag as well. Indeed, as Neil points out, you can use the standard unit, as it were, without those extra features for a discard load, but by using an autoclave with those extra features, a discard load could be processed more quickly. Another example of the type of loads, utensils. Examples like this are metal, plastic, glassware, perhaps, of particular shapes. Those we can treat as glassware. They're solid items in contrast to items that have been wrapped into a into a surgical pouch. This now moves towards acting as a porous load. So what we wouldn't be able to use for this type of item, which is, you can see here, in a pouch, in a porous pouch. What that will do is prevent any physical contamination of the item when it comes out of the autoclave before it's used in a surgical operation. But you've got a barrier there, and that barrier has to allow steam to penetrate in to decontaminate the sterile item. But at the same time, that porous membrane will remain moist at the end of the cycle in a wet autoclave. So we can't use this type with the heating elements inside and the wet conditions inside the chamber. We need to prevent that. So we move to the dry system, which is the one with the steam generating outside, the vacuum system. Oops, I shouldn't press that one. And then the chamber mechanism for heating as well. This is what we call the dry system. And you can only use the dry system for pouched items. Also, the final sort of type of load, which is genuinely fabrics and textiles. They are clearly, evidently, a porous type of item. Those systems would require a dry system with the enhancements we touched on, the external generator, the dry system. But in this case, you might think, well, okay, you've got your dry system, but how do you prove you've had full steam penetration during this process? And you might have to include a test mechanism, which in this case for textile materials is often used, called a Bowie-Dick test, whereby you put a heat-sensitive, steam-sensitive item, a test card inside the load and check for the result before and after. And then you can prove that you've had full coloration of the item of that test card, which will give rise to the evidence of the full steam penetration within the load. But then thinking about that concept of sort of evidence of full effectiveness, coming back a couple of steps, how do you prove on a media load that you've had effective sterilization? Well, this is where we get into load validation or performance qualification, PQ. It's normal in a setup, even though we've talked about these nominal 121 for 15 minutes. That's the sort of default setting. But you can test you can then go a step further and prove evidence of that effectiveness performance by covering filling the chamber with many thermocouples in the initial phase of the testing process, the load validation process. And you will log that, take those thermocouples, there's up to 12 thermocouples inside the chamber, feed them through the sidewall through a pressure restrictive valve, and that allows you to log the data. And now you can use that data, write a report, show that the variation in temperature is minimal, and you've got your audit trail to prove that you've got a load validation process or a performance qualification, part of your IQ, OQ, PQ process. You'd set that into a written SOP, basically decides how many bottles of which material and how much liquid, and that's your SOP. You could do it again for a different size bottle, for a different number of bottles, different type of media, and you then rerun the same load validation protocol. And you do each one of the sizes of bottles, each individual type of load, until you've got a whole set of SOPs for all your load validation protocols. And that's your evidence. And if during that process the engineer discovers that there isn't a successful result, then he will change those settings. So instead of the dreaded 121 for 15, it might change to 123 for 20, or any other permutation of subtle differences in temperature and time, because that would be the specific requirements of the materials involved. It might take longer to heat up. It might take longer for the sort of stabilization of the material to reach that temperature. That's when the expertise of the load validation process kicks in, and we can change the settings subtly to prove that the whole process has been successful. And that's commonly the typical requirement of pharmaceutical companies, PQ load validation surveys, to provide that documentary evidence that the unit not only has completed the cycle, but the load has completed the cycle successfully as well. So there's a key word here, I'm sure you know this, but load validation is with a full load of item, the sample itself. An autoclave that was being calibrated would be completely empty. So you do a calibration in the factory at the manufacturing stage. You might carry that out on site to prove that it had been delivered and installed correctly. It's part of your IQ, OQ really. And then you go from calibration empty to load validation full. And that's your difference between calibration and validation. Just as final thing, I'm just running over slightly, this thing I mentioned right back at the beginning about liquids. So we've done the clean liquids, the bottled media in the Duran bottles. But if it's dirty media, there is a potential alternative way of doing it, because at the moment you load your clean bottles into the autoclave as you would your dirty bottles of liquid into the autoclave. But there is an idea that we've come up with whereby you literally pour the liquid into a receptacle at the top there, that's representing a sink, and it falls down from the top of the unit, from the sink area into the initial holding tank, and it waits there until it starts a process. And underneath that is a secondary chamber, which we call the kill tank, and that effectively is the alternative to an autoclave. That's the high pressure, high temperature section of this process. So that bit takes that liquid up to 100 and whatever for 20-30 minutes, reaches those sterilization temperatures, allows you to ensure you've killed the bacteria, all the proteins are denatured, and then it can just flow automatically to the drain. So the practicalities of this are, there's some angles where you could look at the practicalities of loading an autoclave, unloading an autoclave. This one, you just pour the liquid in at the top and it flows out immediately into the drain at the bottom. The validation process for this one is we use a little cell. You can just see it in the corner there, a little probe whereby we have a sealed port. We put a little live bacteria module into there, and we will take that out at the end of a cycle, incubate it, check for the standard bacteria is killed, and now we've got a validatable process for ensuring that all the liquids in that process have been through the necessary high temperature part of the process. So that's how much are we doing on? So it's pretty much I'm sort of 5 or 6 minutes over my allotted time, but hopefully we've got time for some good questions now.
Thank you very much for that, Paul. That was really helpful.